Okay, let's continue where we stopped last time. From where we stopped last time, we were talking about the process scheduling in the interactive systems, and we were talking about the dynamic priority adjustment and the other stuff. Let me start from a few slides back. We said that for the I/O-bound processes, we like to boost the priority, because when the I/O-bound processes, the I/O-bound processes are blocked more often than the CPU-bound processes. That's why they need more CPU time. For these processes to get the more CPU time, then we need to boost their priority by the fraction of this much, 1 over f, where f is the let's say if the process uses if the process uses only 1 over 2 of the quantum time, okay, if the process uses only 1 over 2 of the quantum time, 1 over 2 of the quantum time, then we make the priority of this process 2, because it didn't use the whole quantum time. It needs more time. But if it uses 1 over 1 of the quantum time, then it means that it doesn't need any more time. So the priority of this one becomes 1. So you take this number and you make it the priority, okay? You take this number and you make it the priority. That's what we discussed last time. The I/O-bound processes needs to have this kind of a priority boost. Then we have the rank queues. That means that we have a small picture here. Each priority class has their own queue, okay, or list, and you run the top priority class. You run the top priority class first. Whenever these are done, then you run these, then this, then this. So you will never run priority class 3 without finishing all of these processes first. Okay, that's run queues. Each run queue is a linked list. To raise or lower a process priority, move it to a different list. Let's say I like to make this a higher priority, so I'll take it here and link it at the end of this one. Okay, so and again for the aging, to change the priority of these systems of the process, there are two things that we can consider. If there are lots of processes in the queues, then we move the whole queue from one priority class to the next priority class. So okay, what we do is just take this one and connect it like that. So the whole queue becomes a higher priority. If we have many processes, if we have only a few processes, then we don't need to do that. We can increase or decrease the priority of the queues, priority of the processes, by only considering the process itself. Fine-grained counter for each process. For this one, we have a fine-grained counter. But if we have many processes, then keeping this counter might be expensive. Then we move the whole queue to the upper level or lower level. This is called the run queue. Okay. So continuing with the scheduling concepts with the interactive systems. Remember, the quantum is the amount of time each process has it for itself without blocking. So if we change the quantum amount, that's the quanta is what is quantum, what is quanta? What is the difference between quantum and quanta? Quantum is, what is quantum? The amount of time each process has on the CPU, right? That's the quantum. What is quanta? Quanta is the plural of the quantum. It says many quantum. Since these are from old Latin days, I mean, you don't say quantas or quantums, okay? You don't say quantum, you say quanta, okay? So varying quanta means that we can change the quantum duration. Many processes need just little bit of CPU time, but little bit CPU time means that you are gonna switch between the processes a lot, and switching between the processes is not cheap. It is expensive. So they say that okay. But what was the problem with the larger quantum times, longer quantum times? The problem with the longer quantum times?
Prosesin işinse bile idle olarak
No, that's not. No. Somebody else will say same thing, and that's not a problem. Because when the process is blocked, you switch already. There's no problem. That's why IO-bound processes need more priority, because they block very frequently. So you increase their priority so that they can run again. Okay, that's not it. No. So what is the problem with the large quantum times? I asked exactly the same question last time, 2 times. Somebody answered actually. What is the problem with the longer quantum times? Smaller quantum time means that loss of switching, that's bad. Larger quantum times, yes.
Makes the IO slower, IO processes.
Makes the IO
reaction time.
Yeah, yes, as an effect, yeah, you can say that. I mean, if the quantum time is large, then when an IO bound job gets turned, okay, then it immediately blocks. Then the CPU bound job runs for a long time. Then it takes more time to the IO bound processes to take its turn. So it takes more time for the processes waiting at the end of the queue, because now I have to wait longer quantum times, right? So that's bad for the processes waiting at the end of the queue. That's why they say that, okay, let's make it varying quanta, okay? Solution to both problems: give lower priority queues longer quanta, okay? High priority queues have smaller quanta. They can switch immediately because they need to be responsive, and low priority queues, they have larger amounts of time, longer amounts of time. For example, they say that for the top priority queue, they have one quantum quanta, okay, one quantum only, let's say 50 milliseconds. For the second queue, you have 100 milliseconds. For the third queue, third priority queue, you have 200 milliseconds of quantum time, okay? So the solution is varying quanta. It's like counterintuitive, but it works. Give smaller amounts of quantum time for the high priority jobs and larger amount of quantum time for the low priority jobs. Okay, so that's what they do. Okay, alternative solution: short quantum at high priority and long quanta at low priority thereafter. You can change the quantum time for the processes. Okay, any questions? Then I will continue. We can remember the problem with the longer quantum times is it takes more time to take the CPU time with the longer quantum times. For the interactive processes, it's a problem. So if the process is an interactive process, then keep the priorities higher. That's what we can do. So how do we understand which process is interactive and which process is not? So this is the solution. If the user is using the keyboard, doing something like that, okay, just get the events from the keyboard, and if the user is creating so many keyboard events, then that means that it's an interactive process. Otherwise, it's not an interactive process. So keep the priority low. Otherwise, increase the priority. That's the solution that the system did. So what would be the problem with this solution? Count the number of enters. Count the number of enters from the keyboard. And if it is high, then it's an interactive process. Keep the priority up. What would be the problem? Yes.
Not all the I/O processes use keyboard. Most of them uses GUI, and they.
Yeah, that's true. But we are trying to help the interactive processes here. I mean, you are saying that. I mean, we should not. I mean, okay, we should keep the interactive process priorities higher, but there are other processes that should be kept higher. Yeah, that's true, but we are trying to keep the priorities of the interactive processes higher. But if you do this, there is a problem. You are in a mainframe, okay? Hundreds of people are using it, and the mainframe operating system tries to keep the priorities of the interactive processes high. So what does it do? It counts the number of keystrokes. If people are doing this, they are doing just this without needing any enter characters. Okay, they just press any of the buttons like that. So all the processes becomes interactive, right? So everybody has a higher priority. If everybody has a higher priority, that means that the system is going to switch a lot. That's bad for the whole system. Okay, so they've been doing this. They were fooling the operating system, making it think that it has a higher priority job. Okay, so process priority. What processes should we have? What processes should have higher priorities? Administrative issues, operating system issues. Okay, and kernel processes. And interactive service processes. These must have high priority processes. Otherwise, the system cannot continue its tasks, or the interactivity of the system goes down. Okay. In Unix or Linux, you can lower the priority of your own process. Okay. You can lower the priority. If you want, you can lower your priority, not higher but lower. And because it's your system, right? Just to help other processes to complete its job more quicker. The command for this one is nice. Nice. You know this command? Nice. When you say nice plus 20 ls, it runs the command ls. Okay, list of the directory. But it runs in a lower priority task. It runs it as a lower priority task. You can lower the priority of your process using this nice. You cannot make it higher. Only if you are the administrator you can make it higher. Only if you are the root you can make it higher. But you can make it lower by making this one. Negative number makes it higher priority. Positive number makes it lower priority. Okay. Traditional in Unix, lower numbers indicate higher priorities. Okay, and the default is 0. It doesn't do anything. Okay. And this is a Linux priority listing. Some of the processes. Okay, these are the processes, and these are the owners, and these are the priorities. Okay. Remember, the lower priority is the lower number is the higher priority. This one is higher priority. The lowest one is this one. So in Unix you can get this kind of numbers using commands like ps processes. Okay. Use this command ps minus. It has many options. With this one ps minus ef, you get lots of information about your processes. By the way, you are going to implement something like that in your new homework because you have many processes. Did you see the homework? Did you get the news? Okay. So this homework it will take much more time than the first one because it has many. I mean, code-wise, maybe it won't take more than 500 lines of code, maybe a few hundred, only that. But it will take more time because processes and the parallel running processes and your own processes, and there are some things that you need. There are some things that you need to design. So it's going to take lots of time. Maybe not CPU coding time, but thinking and design time. So start early. Okay, so these are some of the Linux processes and priorities. And let's continue if there are no questions with the other concepts in this topic. We are talking about the scheduling concepts with the interactive systems. And remember that with the mainframes, there was a scheduling method. It's called the shortest process next. Shortest process first, right? Shortest process first. We can do the same thing. They say that we can do the same thing with the interactive systems. Okay, with the interactive systems or multi-programming systems. It's called shortest process next. The problem here is that in the mainframe systems with the batch systems, I most of the time know how long it's going to take for a batch job to run, to complete, okay? I know how long it's going to take. For the interactive systems, it is difficult to know because the processes are so small and they can change with the parameters and etc. So what they are doing is that they measure how many seconds it took for that process to run last time. Okay, let's say the process ran and it took t0 seconds in the first time. Second time it took t1 seconds, then t2 seconds, then t3 seconds. Okay, so they are saying that we can use these numbers to estimate how long it's going to take next time it runs. Okay, how long it's going to take in the next run. So they said that we can use this formula. Number alpha is between 0 and 1. Alpha is between 0 and 1. Okay. Alpha is between 0 and 1. They say that, okay, to estimate the number for the T2, when I have T0 and T1, I would use this formula. Okay, I would use this formula. Let's say alpha is 0.5, then 0.5 times T0, then 0.5 times T1. Then I estimated. I estimated T2. When I estimate in T3, I can use this. Okay, 0.5 times 0.5 times T0, then this, then this. So as you see, the most important number here is the T2, then T1, then T0. Okay, so the closer numbers to me, okay, the closer the number to me, higher effect is going to have in my estimate. So they'll be using this formula. They say that for each process, I can estimate how long it's going to run. When I know how long it's going to run, then I choose the shortest process next. Because remember, when I choose the shortest process, it would lower the turnaround time, right? Turnaround time would be lower, which is a good thing. So, but some people say that calculating this formula is not that easy because you have many multiplications and many additions and that kind of stuff. When you choose alpha 1 over 2, 0.5, okay? When I say alpha is 0.5, calculating this formula is so easy. All you need to do is this. in order to calculate Tn, okay, what you do is add Tn minus 1 to Tn minus 2 and divide them by 2. That's it. Okay? So that's if alpha is 0.5. That's the good part of the formula. So all you need to do is your previous run and the other your previous estimate and the one before your previous run and the one before the one before that. And this is an actual measurement. This is an actual measurement, and this is the estimate. Okay, and add these two, divide them by 2, and you get this estimate. Okay. Next time you use it and continue this way. It becomes a very easy to calculate formula. So this formula is used a lot. Aging formula. Okay. Aging formula. Aging formula. Okay. So again, this is the same as what we did with the batch systems. Batch systems, we were lucky because they were batch systems. I run them every night, and I know how long they will take. I can calculate it. Million customers, and I'm going to calculate the interest for each one, and it takes 0.1 seconds for each per customer. So that means that it's going to take 2 hours, right? I would know it. But for the multi-programming systems, okay, interactive systems, estimating how long it's going to take for a process to run is not that easy. So I estimated using this way. Shortest process next. Yes?
In a batch system, if our program is buggy, I mean, last 100 times it's run for 2 hours or 3 hours, but last time I ran it run forever, I mean.
Yes.
So what will the system do it?
I mean, if you don't have any preemption,